online. That's the first time I'm doing this, so that's still a bit strange to me, but we'll see how it goes. Yes, so I'm Servann. I'm working in the group of Magdalena Titirici at Imperial College, and I'll just share with you some work we've been doing with activated carbon nanofibers from Lignin and some application in supercapacitors. Do you see my pointer, by the way, or?
Yes, we see it.
Yeah, awesome. Just to give you an overview, I'll talk about energy storage and the place that supercapacitors have in energy storage. Then I'll explain a bit why we use lignin, some advantages of using electrospinning for salt activation. Then I'll talk about some tuning properties of the nanopores that we've been observing thanks to oxygen groups that allow faster charge and discharge of the devices. And then I'll talk about some work on trying to improve the density of the materials for better volumetric performances. And then just if I have some time left, I'll just touch in some graphitic nanofibers, the synthesis, the properties, and some performance that we've observed. Just before this, there is some building works next door. So if you hear like the massive drilling of or some work, just don't worry. This is just me. So I hope you're all staying well during the lockdown. This is of course a very sad period for most people, but also it's quite of an interesting one research-wise, because it allows us to look at also the environmental benefits of basically a massive reduction in human activity. So you can see here that's a graph that was published recently that shows basically the change in global emissions on the axis with various historical events. You can see the financial crisis of the subprime here in 2008 that led to nearly 2% reduction in CO2 emissions. And here the estimated impacts of the coronavirus crisis are estimated to lead to 6% drop in 2020. Of course, we're thinking that this is massive, but if you're aware of the Paris Agreement to try to limit the rise of the global temperature by 1.5 degrees, this means that these global CO2 emissions would need to fall by 7.6% every year for the next decade. So I think this gives us a very good idea of the challenges that's ahead and how hard it will be for us if we want to survive as a species. So you probably already know these graphs. It's the greenhouse gases emission by economical sector. We can see that we have a fourth of it that's generated by electricity and heat production, a fourth by agriculture, and then transportation and industry. And of course, by gases, we can see that carbon dioxide is by far the most emitted greenhouse gas. So we're having different strategies to tackle these problems. One of the strategies is to look at transportation and what we can do to make transportation cleaner. And as you all know, there has been a massive increase in the lithium-ion demand, and most of it here in the blue graph corresponds to passenger electric vehicles. And the problem leads to currently having a massive depletion of the resource, since lithium-ion require cobalt and other type of rare materials. That's a map that I really like. This was made by the RSC a few years ago, I think, and it's basically the Mendeleev table, but showing the abundance of certain elements, and that shows that basically all the elements that are in our phones are with this white symbol here, and we can see that loads of them are endangered. So the whole challenge here is to try to look at sustainable materials and with abundant elements. So just to touch down a bit on how to store electricity, there are 4 common ways to store electricity. There is On one side of the spectrum, the batteries that are well known, and on the other side of the spectrum, we have the supercapacitors or electrical double layer capacitors. And here you have basically their electrochemical signatures. So these are cyclovoltammograms. This means that you basically charge the device by controlling the potential and you observe the current. And here you charge the device by controlling the current and looking at the potential. And here what characterizes batteries is this peak in current, a specific potential that corresponds to this plateau on the galvanostatic charge discharge. And that corresponds to the intercalation of ionic species and the change of oxidation states. And that's what you can see here in the lithium-ion batteries. You can have, upon charge, the lithium ions inserting into the graphite anode. On the other end, the capacitor has a very different CV signature. It's totally rectangular, and it has a linear relationship between potential and time. And that is because supercapacitor stores charges only on the surface of porous electrodes, and therefore we don't see any phase change or irreversible ion adsorption. And of course, this leads to massive changes, massive differences in energy density and power density. Here you can see at high energy density, we have the lithium-ion batteries, lithium-sulfur, also the engines, but then they fail at providing very high power density. And supercapacitors have relatively low energy density of approximately 5 watt-hour per kilogram, but manages power density up to 10 kilowatts per kilogram. And so that is very important because we are trying basically currently to bridge this gap between high energy and high power and try to basically invent devices that can charge and discharge very fast, but also that can store a lot of electricity. And that is basically the role of the pseudocapacitors here that can function either with surface redox or intercalation. And basically, without going too much into detail, what defines supercaps is that you will have always the current here that is proportional to your scan rate. Whereas in a battery, you will have a diffusion limited system where your current is always proportional to the square root of your scan rate. So how does a supercap work? As I said, we have 2 electrodes of the same or a different type. It's usually a porous carbon. And upon polarization of your electrodes here, you will observe that your electrolyte ions here will store into the pores of your electrolyte. And here we have a separator that avoids having a shortcut between your positive and your negative side. And here, this is the double layer charging. This is basically all the charge that are inside your electrode that are formed by electrons are going to be screened by your electrolyte ions. And since only one monolayer of ions cannot fully screen the charges of your electrode, you will have also a diffuse layer, which is composed of a concentration-dependent layer of ions that is driven towards the surface. And that's how a device looks like. So you have your 2-sided electrodes, where usually your carbon powder is coated on a metal foil, and your porous separator, and you can basically wind up these layers and make a cylindrical device like this. Now, the big difference with standard capacitors is that with the electric capacitors, you don't use any electrolytes, so you're able to go at really high voltage, but due to the low density of charge carriers at the interface, you will have really low capacitance. Whereas for supercapacitors, this is exactly the opposite. With with an electrolyte, we can't use high voltage, but due to the presence of ions, we have really high density of charges at the interface, which leads to high capacitance. So what I'm going to talk about here in this talk is more about porous carbons. So we will have electrical double layer effect, but we will also encounter some pseudocapacitance that corresponds to redox pseudocapacitance that we saw in the previous slide, and that is due to the oxygen functionalities on the surface of the carbons. And just to give you an idea of how we calculate, how we relate this to the energy and the power density. So the energy is proportional to the capacitance times the cell voltage square. And if you want to have high power, you need to have very small resistance of your device. And in order to increase the energy density, lots of people have looked into changing electrolytes, basically. So aqueous electrolytes have a thermodynamical or electrochemical resistance of 1.7 volt. But you can put organic solvent that have much higher, or even ionic liquid that have higher resistance. The problem is that if you change, then you also increase the resistance of your device, and that leads to lower power capabilities. So this is how we build our symmetric supercapacitors. We have here our current collectors. We build it, this is called a sweatshop cell. And on these current collectors, we put our carbon electrode here, we infiltrate it with electrolyte, we put a glass fiber separator, and we close the cell. We put the connections directly to the potentiostat, and in the center, we have a reference electrode that enables us to basically watch independently the potential of both electrodes. So why do we need more efficient carbon materials? That's a good question. At the moment, the commercial carbons that are produced from coconut shells because it contains a lot of lignin, and lignin has a high carbon yield. And when they steam activate these coconut shells, they obtain hierarchical carbon structures with meso, macro, and micropores. The problem is that these structures are not really efficient for charge storage in supercapacitors. So for a long time, we've thought that capacitance was only proportional to the surface area of your carbon. So people were trying to develop the surface area here as capacitance is proportional to it. But then we've realized approximately 15 years ago that there is a massive dependence between capacitance and pore size. And so when you decrease the pore size here, going from a macro pore to mesopores, and when the pore size starts to be the same as the ion size, then you start observing a massive increase in capacitance. And that is because here the charge screening from the pore walls is made by the ions, but the ions are solvated. And so basically this debye length, which corresponds to the distance between the unsolvated ions and your pore wall, is relatively large. Whereas if you arrive in, if the ion inserts into narrow micropores, it will desolvate, lose some of its solvent molecule, and therefore the wall ion distance will decrease. And if D decrease, then the capacitance increases massively. So why do we use lignin? Well, as you all know, lignin is in most biomass, up to 40% in some trees, 5% in some grass. And basically in each tree, if you look at the plant cells, you have inside all of the sugars and the proteins. And in the plant cell walls, you will find the polymers such as lignin and cellulose. Now, lignin is a very complex polymer that is made out of 3 monounits. Let's call them G, S, and H. And they are very arbitrary bond to each other, depending on the climate, of the growing conditions, and on the plant species. Currently, lignin is produced in extremely high quantity by the paper industry that transforms the wood into a white pulp from which they are making the paper. And they just break down basically the biomass thanks to this craft process that's using sodium disulfide and sodium hydroxide. And here there is the stream of lignin that is not used to make the paper, but that is used basically to produce the heat and electricity for the whole industry. And this production worldwide corresponds to 70 millions of tons per year, so that's really huge. And 98% of this is burned for heat recovery. And with the 2% remaining, we're trying to find lots of applications because lignin is very functionalized and it's the only aromatic polymer that we can find in nature. So there are loads of potential applications as fuels. These fuels would probably cost a huge amount if we would be trying to make them from fossil fuel. But it finds also applications in thermosets, in adhesives, binders, lignin carbon fiber, what we will see today, and loads of other things. Interesting to note is that during the craft process, these really harsh chemicals transform the structure of lignin by adding some sulfur groups into the structure. So what we're doing in our group is using an organosolv lignin that's extracted not by the craft process, by an organosolv process. I can come back to explain a bit more in detail later. But basically, we dissolve this lignin into an NaOH solution of relatively low concentration. We add a bit of polyethylene oxide to facilitate the electrospinning, as it will align the lignin branches and facilitate the extrusion of the Taylor cone. And here we have a power transformer that puts this metal collector, that's basically a metal foil, at the ground level, and here at 20 kilovolts, and basically it will pull out the drops and start creating a jet of fiber. Now the solvent will evaporate, and what we obtain is a mat of carbon nanofibers, approximately 500 nanometers thick. And then we do a pyrolysis. We obtain this fiber surface, and that is basically the NaOH salt that is activating the fiber that still remains on the surface. So we wash it by putting the mats in water at 85 degrees. And then what we obtain is a porous carbon nanofiber. So we've been trying to look at a little bit what is the interaction between the sodium hydroxide and the lignin. And so by using this solution, we either electrospin it, and just after electrospinning, we start observing loads of small crystals here on the surface of the nanofibers. And when we take this solution, and we don't electrospin it, but we just cast it into a standard glass plate, as it is usually done for standard activation procedures, then we observe that these crystals are actually massive. They are like micro-sized, and this is the EDS picture showing the presence of sodium in the salt crystals. So we've analyzed using XRD those crystals on both the fibers and the casting powder that we call AC powder, and we can see that this is sodium carbonate. We probably also have the presence of sodium hydroxide, but since some of it is amorphous, then we couldn't really assess the presence of it. And then after carbonization and washing, we measure the nitrogen sorption, and we can see that for the carbon fibers, we obtain really high microporous surface area of 650 square meter per gram, versus for the casted powder only 60. I'm saying here really high surface area, not compared to the literature, but just compared to the amount of salt that we have inside the solution. And we explain this because in the AC powder, basically the slow evaporation of the solvent leads to slow crystallization of the salt, and therefore the interfacial surface between the salt and the lignin will be fairly low. Whereas for the carbon nanofibers, we have really fast evaporation of the solvent within approximately 100 milliseconds, and therefore we really interpenetrate the salt inside the lignin structure, and that gives rise to highly efficient activation process. And just to give you an idea about the quantity of NaOH that corresponds to the polymer source, in our work we use 1 of lignin PEO, and then the NaOH corresponds to 10% of this quantity, whereas in standard procedures, people, as you know, they use between 2, 4, and 8 times more salt than polymer. So this is an interesting way, basically, to make more efficient the activation process, let's say. So then we tested this in supercapacitors, and we can see the cyclovoltamograms. thermograms. They are fairly rectangular, as I explained in the second slide. And the powder shows much lower capacitance compared to the carbon nanofibers. And here you can see a slight hump on the CV that is mostly due to oxygen surface groups. And we can see that at higher scan rate, 2 volts per second, we maintain fairly well this rectangular cyclovoltamogram. That is the galvanostatic charge discharge, where we observe a fairly triangular charge discharge. And compared to the powder, the discharge time is much higher. And if we look at the rate capability, the capacitance of the carbon nanofibers is much higher compared to the powder that exhibits only 10 farad per gram. And that leads into high energy density for the carbon fibers, approximately 10 watt-hour per kilogram, whereas the powder is really poor. So we've tried to improve a little bit this system by taking basically the same recipe, but instead of doing direct pyrolysis and then salt washing, we submit the mats to air oxidation at 200 degrees for 2 hours, and then we do the pyrolysis. And so we did some XRD. We still have these sodium carbonate crystals. And here, by doing FTIR, we show that there is the presence of an oxygen peak here at 1730. That tells us that the carbon fibers has probably been oxidized. Here you can look on the XPS spectra. On the carbon here, we observe the presence of a higher amount of ketones and carboxylic acid groups here. And on the oxygen side, we also observe the increase in oxygen groups here. The increase is not really high, so we see here the 20% oxygen, and here for the non-stabilized sample, 18% oxygen. But we will see that this is enough to change totally the ion diffusion inside the micropores. And this is basically a scheme that shows the oxidation of lignin that has also been shown by some peers in the literature. So if we look at the non-stabilized mat, here we have nanofibers of 400 nanometer. The stabilized mat shows slightly smaller diameter because since it has higher oxygen content, you have also higher mass loss and lower yield, so that decreases the diameter. If we look at the surface area, we have approximately the same surface area. I mean, you also experienced in calculating surface areas, and that's we all see that this is highly. It's quite hard to obtain exactly the same results. So I would say that is fairly similar in terms of pore size. We also have a similar pore size that's around 0.6 nanometer. 0.6 nanometer just compared to a standard aqueous electrolyte ion that's approximately 0.3 nanometers. That's fairly close. And if we look at the XPS, we can see that we have slightly higher oxygen content here in the stabilized sample. And if we do some TPD, that basically investigates the amount of acid groups by the evolution of CO2, or the amount of basic groups by the evolution of CO, we can see that the acidic groups are fairly similar, whereas the basic groups, the stabilized samples has much more many basic groups here, and particularly ketones and carbonyls, which have shown to be particularly efficient for pseudo-capacitive storage. And here, that is, we measure the supercapacitive performance in 2 different electrolytes, in 6 molar KOH and in 1 molar sulfuric acid. And we see that in KOH, the performance of these 2 samples is very similar. That leads to the capacitance of 200 farad per gram and a fairly good capacitance retention at high current density. And here in sulfuric acid, we observe a massive difference in performances, where the stabilized sample maintain really high capacitance, but the non-stabilized sample has fairly low capacitance. And so we've been wondering why is that? Why such a small difference in oxygen groups could allow such a big difference in capacitance retention and energy density. So we cycled the device 10,000 times, and we observed that for the non-stabilized fibers, these capacitance slowly increase until 125%, and that whereas the stabilized sample is fairly stable. And that basically tells us that this sample is not very well wet. So there is a low accessibility of the electrolyte ions to the porous structures. And this is why the more we cycle the device, the more the electrolyte is able to penetrate the porosity. So we decided to look a little bit more into this and perform some impedance spectroscopy. So just for some of you who are not really familiar with the technique, this is basically applying an oscillating signal on our device between the working and the counter electrode, and in this case we apply potential. So the potential is sinusoidal curve, and then we observe basically the trend that the current has, and we measure the dephasing angle. And the impedance, which corresponds to the resistance of the device, depending on the frequency, will be calculated by doing V over I. And then as both of these values are complex values, we can basically write the impedance over time is equal to a real component and a complex component. And here is a little scheme of a typical hierarchical carbon, where we have large mesopores, smaller mesopores, and then small micropores, sorry. And we can see that as the frequency is really high, we have no penetrations of the ions inside the micropores, because they are basically going from the counter to the working very, very fast, and they don't have time to penetrate. So the highest capacitance and the highest accessible surface area will be available only at low frequency. And that is the Nyquist plot that corresponds to the complex impedance here on the ordinates with the real impedance on the axis. And this part corresponds to the high frequency, and this part corresponds to the low frequency. And that is shown that for different electrical components, such as the resistance, this Nyquist plot will be only one single point, because the resistance, the impedance of the resistance is independent of the frequency. The impedance of the capacitor is dependent of the frequency, and this is why you see, as the frequency lowers, an increase of the imaginary impedance. If you put the two of them in series, then you will start observing this system, where that is the value of the resistance. And if you put the two of them in parallel, you observe this typical semicircle. So what we observe in most supercapacitors when you do impedance is basically a semicircle that corresponds to the interface. So it depends which interface you're looking at. And then a vertical line that is not always exactly vertical, but that corresponds to the capacitive domain. And if you have a region in between these two semicircle and vertical line that is kind of a line, or that is not really a semicircle, then it's probably meaning that you have a diffusion limitation in this range of frequencies, and that can tell you a lot about your post structure. And this diffusion limitation is basically given by this Warburg component here on the electrical circuit. So we look at the Nyquist plot. Yeah?
You have 3 minutes left?
3 minutes, okay. Yeah, I'll be quick. So here the Nyquist plot is showing that in the case of acidic conditions, your non-stabilized sample basically shows exactly this diffusion limitation. And that is why we have really poor performance in acidic conditions. Here, if you look at the relaxation time, that tells you basically how fast you can charge and discharge your device. And here you observe with the plain lines that you have the same relaxation time in basic environment, but much faster relaxation time in acidic environment. And that is the energy density for all of these carbon fibers. Shows you that it's much higher than typical supercapacitors already on the market. So just very fast, as I'm lacking a bit of time, we try to increase the density of the mats because the problem of these mats is that they have really low density. And basically, we tried pressing these mats using 40 bars into much more compressed systems. Those are the X-ray tomography. And we managed to increase the density of these mats by 6 approximately. That is showing you basically when we press the mat at different pressures that we can merge these fibers into a film. So that's not really what we want to do. So that's why we chose 40 bars, because it seems like a good compromise between the dense mats where we can retain this fibrous morphology. And you can see also the growth of these crystals here on the surface of the fibers while pressing. And so the last slide. Here you can see that the press sample here or the non-press sample have pretty similar electrochemical performances. But if you look at the volumetric capacitance, which is important because it tells you about the packing ability of your device, is much, much higher. And if you look at the relaxation time, which is how fast your device can be discharged, it's also very similar. And that tells you the volumetric Ragone plot tells us also that the volumetric energy has massively increased. Of course, it's not nowhere as close as the graphene-based supercaps, which are currently being commercialized, but this is a first step towards sustainable lignin-based dense electrodes. And that, of course, I don't really have time to go over it, but if you have any questions, we can talk about this. And yeah, sorry for the rush towards the end, and thank you for your attention.
Thank you very much, Servann, for your presentation. I guess a lot of stuff for a lot of the audience, or at least for me, because my electrochemical knowledge is, let's say, limited. If anyone has questions now, please write it in the chat. I think we can still take some minutes. If anyone wants to ask.
Yeah, I tried to make it somehow a bit understanding, because I know not everyone is an electrochemist, so it was hard to pack everything.
So maybe because it's usually, or at least if you work with Porosity, one of the main things is, so what's your yield for your or the yield difference between your air stabilized carbon nanofibers and the non-stabilized ones?
The yield difference is not really high. It's like 35% for the non-stabilized and 25% for the stabilized.
Okay.
Yeah. So it's still quite low compared to, I mean, given this quite small amount of salt that we have. But that we believe is because we improve basically the activation process.
You got one question. So how does the oxygen functionality of the mats affect their performance? Was the question.
So this is kind of, that's a perfect question, but it is very hard to know exactly how this is happening, because we would need to look at really into the nanopores, and that's a bit tricky. But what we believe is just that the presence of oxygen inside the micropores is basically facilitating the movement of ions towards the entrance of the pores. And yeah, basically this. So that the more oxygen you have on the surface, but not only on the external surface, you need to have also oxygen inside the nanopores, so that your electrolyte ions will have, it will be more easy for them to insert. And I guess only a small percentage also manages to do the job.
Okay, then I would say, as we are already short in time, thank you again, Servann, for your presentation.
No problem. Thank you very much.